right? So what we had learned that if we are changing the state of the system only without altering the kinetic energy, then the work done by the external agent will be equal to change in potential energy. Whereas in general, if we are also changing the kinetic energy of the system, then the total work done will be equal to the change in kinetic energy plus change in potential energy. Okay, so that statement we came towards the end. So I'll come to that also. Okay, so to understand the logic of that we have to basically go back to this thing, that if the external agent is acting in such a way that it is only changing the state of the system without changing the kinetic energy, okay, that means the work done by the external agent, which is equal to delta U, or the change in potential energy, it is equal to the work done against the internal conservative force. So that's the example that we saw, that if a spring is being pulled very slowly or being pushed very slowly, whichever case, such that the kinetic energy is not changing, then whatever work is done by the external agent, it is the work done against the internal force of the system, which is the spring force, the internal conservative spring force. So the work done by the external agent, which is equal to the change in potential energy, it is also negative of the work done by the spring force. Okay, so that's how we get the relation, that what is the relationship between the work done by internal conservative force and delta U, change in potential energy. And that relation is written over here, that delta U is equal to negative of work done by internal conservative force. And this is a universal statement. This will apply, okay, whatever be the case. Yeah, so change in potential energy has what relation with, so this is the statement that explains that, okay, that when the external agent is doing work in such a way that there is no change in kinetic energy, then in this relation on the left hand side, you can see W external is equal to delta U. But also you can understand that the total work done is equal to 0 because there is no change in kinetic energy. That means the work done by the external agent plus the work done by internal conservative force should be 0. So like going back to that example, when we are pulling the spring very slowly, the external agent is doing some positive work, the spring is doing negative work, and the sum of the two work done is 0 because the kinetic energy of the system is not changing. So now comparing these two relations, you can see that delta U has a relationship with work done by internal conservative force. And that is this relationship that we've written on the right hand side. That delta U for any system is equal to negative of work done by internal conservative force. Okay. And this is a universal statement now. This is irrespective of whether the kinetic energy is changing or not. Okay. If the kinetic
energy, delta U?
Delta U is the change in potential energy. U is the the symbol that we use for potential energy of a system. So delta U is the change in potential energy, right?
Yes, sir.
Okay, so understood this. So this is the you can say the universal definition of potential energy, that in any system, if we are making any change of state or change of configuration, then the change in potential energy will be equal to the negative of the work done by the internal conservative force. Okay. Okay. Now moving on from this, now we come to the statement of work energy theorem proper, that now if there is combination of external forces plus some kind of non-conservative force acting on a system, then the total work done, that is work done by external plus work done by non-conservative force. So this WNC here stands for non-conservative, work done by non-conservative. So the sum of these two work done is equal to what? The change in kinetic energy plus the change in potential energy. So that is the statement of the work energy theorem. Okay. And then we saw that with the application of this particular question. So we'll continue from that point today. Okay. So just a moment, I will go back to the notes of 12th so that I can print and send that to you also. Okay, this will just take a moment. Right, so let's start today by looking at some more examples of the application of statement of work energy theorem. Okay, so work by energy. So we saw the statement of work energy theorem. That is the work done by external force plus the work done by any non-conservative forces is equal to change in kinetic energy plus change in potential energy of the system. Okay. Now we can always compare this to the statement of the work kinetic energy theorem. Yeah, see that we have come to the last concept, which is work energy theorem. And of course, we have to also discuss about power. So one more additional concept, power remaining after this, but we'll come to power after discussing some applications of work energy theorem. Okay. So if we compare this with work kinetic energy theorem, which we had discussed earlier. Okay, so there what we had seen is that the net work done is equal to the change in kinetic energy. But keep in mind that this is applied to a single particle or a body. Okay. And this is applied to a system. There's a slight difference in how we apply this. Okay. So the logic of the comparison here is that this net work done, it is actually the sum of the work done by external forces plus non-conservative forces plus internal conservative forces. And that is equal to change in kinetic energy. So now when you compare this statement with this statement, you see that the relationship is that delta U is negative of work done by internal conservative force. So this is the whole point of it. Okay. So for example, suppose we are having this situation. It is similar to the one we discussed last time, but let's also bring in friction into play now. So if we have a spring attached to a block of mass m, which is on a rough surface with coefficient of friction mu, and initially the speed is 0 and the extension of the spring is also 0. So this is the initial state of this system. Okay. Now what we do is we apply some constant horizontal force like this, and as a result of that, after some time, the spring has stretched by x. The block has developed a velocity v. Okay, so a constant force F is applied horizontally. Okay, such that F is greater than mu mg, so it's able to make the block move. Okay, so when we look at this system and we want to apply either of the two theorems above, so if we first of all, if we apply work kinetic energy theorem to the block, okay, then our statement of this theorem would be that net work done is equal to change in kinetic energy. So that would be work done by spring plus work done by the external force plus work done by friction. This would be equal to the change in kinetic energy. Okay, keep in mind that work done by mg is 0 and work done by normal reaction is 0. So those don't count in the net work done. So this would be our statement. Okay, but on the other hand, if we were to apply work energy theorem, okay, to the block plus the spring as a system, okay, then how would we express that? So we would say work done by external agent plus work done by any non-conservative agent is equal to change in kinetic energy plus change in potential energy. This is how we write this. Okay, so this would be the theorem the way we are writing for this thing. So we have to now convert this. Okay, this, so you see the difference in the statement of the theorems. Okay, and accordingly when we implement this, you'll see how this will change. Okay, so F is a constant force. Okay, so we can see that the work done by the spring will be minus half kx square, because we've seen that formula already. Work done by the spring is minus half k into x final square minus x initial square. Where this was coming from? This was coming from the fact that the work done by spring force is minus kx dx integration. So from that it's coming. Okay, so that we are applying over here. So this is work done by the spring. The work done by the external agent will be plus Fx, because F is a constant external force. And work done by friction would be minus mu mgx, because as the block is moving in this direction, friction would be acting like this, and it would be mu mg. And spring force would be acting like this while the block is moving like this. So the friction would end up doing negative work, and the change in kinetic energy would be half mv square. So this is how we write the statement. Okay. Now I want you to work out exactly in the same way that when we implement this, what is the equation that we'll get, and compare the two. Okay. So just see how we will implement the two over here.
So can you zoom on the diagram? Sir? Shom sir?
Sir,
Okay, so let's check this out. So here we'll get the statement that work done by external agent will be plus Fx. Okay. Work done by non-conservative
Sir,
force.
I didn't understand the question in the diagram.
Okay. What is there not to understand? With a block attached to a spring on a rough surface, and then we are pulling it with a constant force horizontally. So after some time, the spring is extended by x and the block speed has become v. Understood?
Yes, sir.
इस ब्लॉक को मैं पुल कर रहा हूँ विद अ फोर्स व्हिच इज ग्रेटर देन म्यू एम जी ना, तो जैसे ही मैं फोर्स लगाऊंगा यहाँ से क्या होगा, वो एक्सीलरेट करेगा.
Yeah, sir.
Okay. So going from this state to this state, if I apply work kinetic energy theorem, this is the final result that I'm getting. This one. Okay. Where each of these terms you can understand. This is the work done by the spring. This is the work done by the external agent. And this is the work done by friction, which is the non-conservative force. Now, similarly, when I apply work energy theorem, what are the terms that I'll get from the statement? Okay, so we can see that work done by external agent is plus Fx. Work done by non-conservative force of friction is minus mu mg. This should be equal to change in kinetic energy, which is half md square, plus change in potential energy, which will be how much? Half kx square. Because we had seen earlier, the formula of potential energy of a spring is how much? It is half kx square. So here initially x was 0. So initial potential energy was 0. And finally, the spring is extended by x. So now can you see that both these are actually the same? This and this are just the same. Or if you compare this and this, you can understand that what is happening is delta U of the spring is nothing but negative of work done by spring, or negative of work done by the internal conservative force is equal to delta U. Okay, so I hope this is clear, people.
So
Yes,
just 1
sir.
minute, sir. Noting it down.
Sorry, come again.
Just noting it down.
Yeah.
So what is the meaning of x and mu mgx?
X is the extension of the spring, which is the same as the displacement of the block. Mu mg is friction. So the frictional force is acting opposite the displacement. Na? That's why the work done by friction is minus mu mgx.
Yeah, okay, sir. Okay.
Understood? Okay, finish writing this down.
No, sir.
So just last line, sir. 1 second.
Okay.
माझं लेक्चर चालू आहे. काय ते खेळायचं असेल तर विचारा. मी
Sir, why didn't we add the x in the mu mgx below in the work energy theorem part?
Oh, why we have to add it? That term is there, sir. This is minus mu mgx. Both the terms are the same. Okay. Work done by friction is basically minus of frictional force into x. No? So it is. So this is common in both the equations. This term goes here
Yes.
also, and this term goes here also. Just add this x over here. It was left out by mistake.
Sir, after comparing these both equations, we got triangle U, delta U is equals to minus work done by spring. No?
Negative of work done by spring. So it just verifies the relationship between work done by internal conservative force and the change in potential energy. You know. Okay, done now.
Yeah, sir.
Okay. Now, let's see one more example of potential energy. So in this whole chapter, when we apply work energy theorem, there are two standard formulae of potential energy that we have to apply in various numerical applications. One of them is potential energy of the spring, which we derived in the last class, which you've seen in this question. The other standard formula which we will use is the formula for potential for gravitational potential energy. Okay, so let's look at that next. So once we know both these formulae, we will be able to do most of the application questions. Gravitational potential energy, okay, of a body or particle, whatever, of mass m on or near the Earth's surface. Okay. So the idea is very simple. We know the general relationship between potential energy and internal conservative force is that delta U for any system is negative of work done by the internal conservative force. That is change in potential energy of any system, okay, during a change in its state or configuration. Okay. So that equals to negative of the work done by the internal conservative force of the system during that change. Okay. So now, for example, if a body of mass m is, let's say, at some kind of position with respect to the Earth's surface, it need not be on the Earth's surface exactly initially. Even initially, it could be at certain height from the Earth's surface, let's say. It's at a height h1. Okay, this is the initial state. And due to a combination of forces, it's moving along some kind of path. And after some time, it's reaching this final state where it is now at a height of h2 from the Earth's surface. So if I take my system as the Earth plus the body, okay, then for this system, the gravitational force which is mg is the internal conservative force. Okay. So whatever general statement we made above, now specifically for this system, when we are talking about the entire Earth plus the body as the system, then which is the internal conservative force for that system? It is nothing but mg, or the gravitational force. So the change in gravitational potential energy, okay, that will equal to negative of work done by mg, by the gravitational force. Okay. Or what we can write symbolically as delta U gravitational is negative of work done by gravitational force. Okay. Now I can start using proper vector algebra. So I can see that if this is my x and y axis, so if y axis is vertical, okay, then gravitational force, that will be minus mg j cap. That means it has a constant magnitude and fixed direction. So wherever the block is, mg is a fixed force that is always acting vertically downwards. So work done by gravitational force will become what? It will become minus mg dot product with the displacement. Okay. So now if you can see that displacement is like this.
Don't be shy, girl.
If the displacement is some change in x coordinate plus some change in y coordinate, then work done by gravity will become minus mg delta y by that dot product. Okay. Where delta y is the change in the vertical position with respect to the surface of the earth. Okay. So from this now we can see that the formula for delta U or change in gravitational potential energy, that becomes how much? It becomes mg delta y, because delta U is negative of work done by gravity. So work done by gravity is minus mg delta y. That is why when the object's height increases from the ground, okay, the gravitational work done or work done by mg is negative. But on the other hand, what about the potential energy? It increases because the work done by gravity is negative. So that means the delta U should be positive. Whereas vice versa, when we allow an object's height to decrease, so it's coming down, it's coming closer to the surface of the earth. In that situation, the work done by gravity is positive, which means that the change in gravitational potential energy will be negative. Okay, so just make a note of this derivation and formula. And from now, we'll just remember this as a rule of thumb. Okay, that the formula for delta U or change in gravitational potential energy is mg delta y, where m is the mass of the body that is being moved and delta y is the change in its vertical coordinate.
So could you please re-explain that green part all again?
Yeah, so see what is happening in the diagram. You can understand that as I'm moving my body from initial to final position, irrespective of what the path is, the gravitational force is constant. No? It is minus mg j cap, right?
Yes, sir.
So for any constant force, how we define the work done? We don't have to do integration. No? We just define the work done as F dot S.
Yes, sir.
Now, regardless of what the path is, the displacement vector will be some delta x plus some delta y j cap, right? It will have components delta x I cap and delta y j cap. Okay.
Yes.
Where delta x is basically what? It is the horizontal component of displacement, and delta y is the vertical component of displacement. So when we take the dot product of these two, the force which is mg and the displacement which is s, when we take the dot product of these two, what is the quantity we'll get? We'll get minus mg delta y. Just see the dot product of these two vectors, you can understand, right?
But what
So
about the horizontal
this,
component?
sorry?
But the horizontal component.
नहीं आएगा ना बेटा, because देखो dot product कैसा होता है दो vectors का? If you have a vector A which is AX,
okay, sir, got it.
Got it, na?
Yes, sir.
We're just using this formula, na? It is AX BX plus AY BY, na? So
yes,
now the force doesn't have an X component, na? So the dot product, we're just using this. So likewise here, the force we are talking about is just having a Y component. It is mg j cap. It doesn't have an X component. The displacement might be having both components, but then when we take the dot product, the X component will not matter. So that's why the F dot S here for gravitational force will be minus mg delta y. Okay, and next step, once we know that work done is minus mg delta y, so what about the change in potential energy? It will become plus mg delta y, because the relationship between the two is this. Okay, this is the relationship, that delta U is negative of work done by gravity. Okay, so hope this formula is clear, people. So now the general idea that we have is that in any situation, the change in gravitational potential energy as we take a mass of m from some initial y coordinate to some final y coordinate is given by this. Okay, or we can say that final potential energy minus initial potential energy for gravitation is the weight of the object into the final vertical coordinate minus the initial vertical coordinate. So from this we can see that for the vertical coordinate going up, that is y2 is greater than y1, then delta u becomes positive. Okay, and for the vertical coordinate going down, okay, delta u therefore becomes negative. Just remember this like a rule of thumb, that if the object's height is increasing from the ground, that means the potential energy is increasing. Delta u is positive. Okay, so now we can see the simplest way of understanding this through an application question. People, I hope you are clear with this formula. Okay. So let's understand this with an example like this. Imagine we have this, we have a smooth horizontal, smooth inclined surface. Which is at an angle theta. Okay. And now what we do is, we release a block from rest from here at time t equal to 0. So what happens is, after some time, when it has made a displacement of s, it's gained a speed v. So we want to find the speed v for s is equal to, let's say, 50 meters, theta equal to 37 degrees, and g is equal to 10 meters per second square. Now we can see that we can do this question in two ways. One is that we can apply Newton's laws of motion, okay, free body diagram and all that, to find the acceleration of the block, and then kinematics.
So we don't know the time, no?
But we know the displacement, no? So kinematics to find v, uniformly accelerated motion. So there's that relation of v square is equal to u square plus 2as. Yes?
Yes, sir.
Okay. But this is two-step, no? First step to find acceleration, second step and all that. Now much easier we can see here that we can directly use work energy theorem. Okay. And for that, take the earth plus the body as a system. Now we'll notice something interesting when that happens. Our work done by external force is 0, because normal reaction does not do work. Okay. And in addition, what is happening? There's no non-conservative force. So work done by non-conservative force is also 0, because it's a frictionless surface. Because there's no friction here. Okay. So ultimately we'll get that the change in kinetic energy plus the change in gravitational potential energy is 0. So you just have to apply this. So it will become a one-line solution for us. Okay. And you can compare the result of that one-line solution with the equation above. And you can see that even though we don't know the mass of the body, and we will require the mass when we substitute in the work energy theorem, but it will cancel out and it will give us the value of V as a one-line solution in terms of the displacement S. So just work this question out quickly, people. We'll discuss.
Sir, won't mg be a non-conservational force?
No, mg is a conservative force. Na, beta. Yahan pe we are taking Earth plus the body as our system. Na? So mg is in fact the internal conservative force. Na? So that's why it's not showing up on the work done side.
Sorry. Yes, sorry, sir. I took it ulta accidentally.
Yeah.
Okay.
Got it, na?
Yeah, got it.
Okay.
So don't we need to know the height of the particle when it was above?
Yeah, so we will know na beta because we know theta and we know S. Na? So trigonometry se nahi aayega height. Got it, na?
So starting तो हमें x height लेके करना मतलब x distance from the ground लेके करना पड़ेगा ना from the
H1
point of
H2 ले
view.
लो, that is fine, but the difference in height is what we need, na beta. Delta y is what we need, na? The difference in height.
But second वाला distance x minus.
So the difference in height is just going to be like the vertical of a triangle, na? Whose hypotenuse is S. Got it?
Yeah, sir.
Okay, so use that only.
कंट्री कैसे कंट्रोलेशन है कंट्रोल जाना आता है और ये अपना शामिल होगा नहीं आपको बैठेगी आज ये कभी हो जाएगा Computer science, we have given a few seats for dummy type in dummy type. So at least you confirm your college admission. तो एक बार वो हो जाएगा ना सर. Practice पेरेंट्स वो दिमाग में रखते कि चलो 11th तक एडमिशन हो गया.
Okay, so let's see both the methods here. So for example, if I go with the lengthy method, now even that is not so difficult because you know how to solve after all from Newton's laws that this will have an acceleration which is mg sine theta, no? Because there's no friction. So you can see over here that mg sine theta will create the acceleration. Okay, so here that acceleration will become how much? It will become sine 37 component of g. So it will become 6 meters per second square. And of course, normal reaction balance is mg cos theta. This is of no use to us. This is the main equation. Now we can use the relation that u is 0 and the displacement is, we are taking it as 50 meters. So v square is equal to 2as. So from that we'll get the value of v. So 10 root 6 meters per second. This is the v which we are getting. Okay. Now let's see the same thing from work energy theorem. And that is so much easier because all we have to work out is trigonometrically that if this displacement is 6 meters from here to here, and how much this height difference is. So this is 50 meters. And how much this height difference is. This h is going to be s sine theta. So it is going to be 30 meters. So now going from A to B, You can see initial speed is 0, final speed is v. Okay, so change in kinetic energy plus change in gravitational potential energy is 0. So this is plus half mv square, but this is minus mgh because the vertical coordinate is decreasing by h. So we directly have the relation that v is equal to root 2 gh, or v is equal to square root of 2 into 10 into 13, or 10 root 6. Okay. So in this case, we can see it is a more convenient way of solving, though it's still possible to solve by using methods that you learned before work energy. Now, next, I'll show you a question where we have to use only work energy theorem. There's no other way of solving the question. Okay. So that kind of situation can also happen where exclusively you have to use the work energy theorem.
Sir, isn't
Yes.
delta UG positive mgh?
No, delta U is not positive beta. Remember the formula for delta U? Delta U was mg delta y. Because
Yes, sir.
work done by gravity was minus mg delta y.
Yes, sir. So then why do you write minus mgh over there?
Because delta y is negative, na beta. Height of A is greater than height of B, na. So in this particular case, what is happening? My change in y coordinate is minus h, na, from A to B. Isn't it?
Oh, okay. Got it.
Shom sir,
Yes.
can you zoom out? I want to copy both the methods.
Okay. Okay, finished with this?
No sir, 1 second.
Okay. Okay, done. Okay, next example, like I was saying, we will see something where it's virtually impossible to solve this question by any other method. But by work energy, it becomes something very simple. So if we have some unknown curved surface, which is smooth. By unknown curve, I mean the equation of this curve is not known. Okay. But this is in a vertical plane with g equal to 10 meters per second square. And now a particle is released from rest at a point A. And it comes sliding down, and after some time it reaches the point B. And by the time it reaches here, its speed is v. Now also we know that between A and B, if we drop this perpendiculars, the vertical displacement, this part, is 20 meters. So a particle of some given mass, let's say 2 kg, is released from rest at the point A and develops speed v as it slides to the point B. So find work done by gravity from A to B. Change in gravitational potential energy. Again, as the particle is going from A to B. And the speed at the point B. Now this is a smooth surface, so there's no friction involved. So now, as you can see, this question cannot be solved by kinematics because the acceleration will be variable. Why the acceleration will be variable? Because the component of gravity acting along the tangent is not a constant. The angle of the surface is changing all the time. So here, because the surface is curved, that means the angle of inclination varies. So that means that the acceleration is variable. Okay, and unknown also. Because we don't know that angle and all that. So therefore, kinematics cannot be used. You cannot apply kinematics to find V. However, work energy theorem is very easy to apply. But because there is no friction, so work done by non-conservative force is 0. And normal reaction does 0 work. Because normal reactions dot product with displacement is 0 at all points. So at any point of time during this sliding motion, if you look at the normal reaction force, it is acting this sort of a direction, normal to the surface, and the instantaneous differential displacement will be along the tangent to the surface. So they'll be perpendicular to each other. So because of that, we can say that at every point, n dot ds is always 0. So the work done by normal reaction will become 0. So hence, when we apply work energy, we can very clearly, very easily say that the change in kinetic energy plus change in gravitational potential energy is 0. Because work done by external force is also not there. Work done by non-conservative force is also not there because of these reasons. Okay, so now that's very simple. A to B, you can see that the change in kinetic energy is plus half mv square. Change in potential energy is minus mgh. So as long as we know that h, it's very easy. V is nothing but root 2 gh. It should be 20 meters per second. So this is an example of a question where not only we had an advantage by using work energy, but work energy is the only feasible method of solving the problem. Okay, that acceleration and kinematics method fails over here. So there's no way we can find the acceleration as a function of time or displacement or anything, because we don't have any information about that curve. Okay, so we don't have any information about the path. So this
Sir, done.
Okay, so these two last questions you have seen were situations where when we applied work energy theorem, the work done side of the theorem was 0. Okay, the net work done, that is work done by external force plus non-conservative force, is 0. Okay, so the sum of change in kinetic energy plus change in potential energy was equal to was equal to 0. So this particular situation is given a special name, and that is called conservation of mechanical energy, because the sum of kinetic and potential energy, as you are probably aware, is called the mechanical energy of a system. So change in kinetic plus change in potential energy overall is the change in mechanical energy. And if the sum of the two is 0, that means change in mechanical energy is 0, or in other words, the total mechanical energy of such a system is conserved. So this is, you can say, like a special case of application of work energy theorem. Okay. In general, work done by external plus work done by non-conservative is equal to change in kinetic energy plus change in potential energy, where the sum of kinetic energy plus potential energy is given the name mechanical energy or total mechanical energy. Sum of kinetic energy and potential energy. Okay. So change in kinetic energy plus change in potential energy can overall be written as change in mechanical energy. Okay. So therefore, now we see that if we are in a situation like the above two examples, in a special case where neither any external agents are doing work nor non-conservative forces are doing work. So if this is an AND condition, that work done by external is 0 and work done by non-conservative is 0, both these statements are satisfied. So it's an AND condition. Then it implies that change in kinetic energy plus change in potential energy is 0, which implies that the change in mechanical energy is 0, which means that the mechanical energy is a constant quantity. So in other words, whenever this happens, we say that mechanical energy of the system is conserved. So whenever this statement is satisfied, it now means that mechanical energy will be conserved. These type of applications are called conservation of mechanical energy applications.
Sir, could you zoom out a little bit?
Yeah.
Yes, thank you.
Sir, what is the value of work done by gravity and delta U?
Sorry,
So what is the value of work done by gravity and delta U?
in which question you are saying the upper one?
Yes, sir, in this question
that
only.
particle sliding down the inclined plane. Yeah. So see, as
Yes.
it's going from A to B, at A the particle was at rest, na? So the initial kinetic energy was 0, and at B the kinetic energy is half mv square. So the delta K is how much? Plus half mv square. Got it?
Yes.
And going from A to B, the vertical coordinate, it is coming down by h. Na? So our delta U will become minus mgh.
Yeah, sir.
Okay. So even though m is unknown, or actually m is given, na? Yeah. So we will calculate these two also. Okay. So coming back to this, so our change in gravitational potential energy is minus mgh. So that term will become minus of 2 into 10 into 20. So minus 400 joules, isn't it? And now, what is the relationship between work done by gravity and change in gravitational potential energy? Work done by gravity is negative of change in gravitational potential energy. Is this statement clear where this is coming from?
Yeah, sir.
Okay, so work done by gravity यहाँ पे कितना हो जाएगा? Plus 400 joules. Okay. So because gravity is doing positive of 400 joules work, that is why the potential energy is decreasing by 400 joules. And in this case, that's why the kinetic energy is increasing by 400 joules. Okay. So what is happening overall, we can see that work done by gravity is is positive 400 joules. So change in gravitational potential energy is negative 400 joules. So the kinetic energy is therefore increasing by 400 joules. Okay. Okay, now the statement of this conservation of mechanical energy is clear to all of you? Sum of kinetic energy and potential energy is defined as mechanical energy. Okay, so K plus U is equal to E, the mechanical energy. So in our work energy theorem, if we come across a situation, the special case where left hand side is 0, that is work done by external force is 0 and work done by non-conservative force is also 0. Then what will happen is that the change in kinetic plus change in potential energy is equal to 0. Or in other words, the total change in mechanical energy is 0. Therefore, the mechanical energy is a conserved quantity. Now, if the change in something is 0, that means that quantity itself is conserved. Isn't it?
Sir, just try to ask you, sir. So
Yeah,
basically, change in mechanical energy will be external work plus non-conservational work.
yes, yes. Okay, so
Okay.
I mean, another way of writing the same theorem, that work done by external plus work done by non-conservative forces is equal to the change in mechanical energy. Is another way of expressing the same statement as this, right?
Yes, sir.
Okay. So now let us see a question.
Sir, just 1 minute, sir. I'll just
Yeah.
note this down.
Yeah.
Okay, sir. Done.
Okay. So now let's see this next example where we are doing something like this. So what we've done here is, from a fixed ceiling, let's say, okay, we have suspended a spring, an ideal spring. So an ideal spring is always massless. Okay. And we've suspended a block of certain mass from that spring. And initially what we are doing is we are holding this block such that the spring was at natural length and the block was at rest. So we were applying some kind of external force. Okay. And then suddenly we withdraw that force. So initially the block is held at rest with the spring in a relaxed state. That is, x for the spring is 0. Neither there is compression nor there is extension. So given the mass of the block is, let's say, 2 kilograms and g is equal to 10 meters per second square. Also that the spring constant, let us say 40 Newton per centimeter. Right, let's make the mass a little bit more. Let's make it 8 kgs. It's easier to solve. Okay, now what is happening? So we want to find out, first of all, what is the external force we are applying. First part. Okay. Now, second part of the question. Now the external force is suddenly withdrawn. Has made a displacement of x downwards, find a relation between its speed and this downward displacement x. So that's the second part. And third part, using this relation, we'll see, we'll find the maximum extension. X max for the spring. And we'll also find what is the speed at an extension of 2 centimeters.
Sir, F external over here is obvious, right? 80 newtons.
Yes, it's obvious it's initially balancing the weight, because how we know it's balancing the weight? Because the state of the spring is what? X equal to 0, no? So the tension in the spring is 0. So the free body diagram will show us that if we are holding the block at rest, is the external force which is balancing the weight, because the spring doesn't have any tension at that point of time. So that is why F external should be equal to mg. Very obvious answer, like you said, it should be 80 newtons. Now we withdraw that force altogether. So that's when the motion of the block starts. So by the time the block has come down through a distance of x, okay, the spring has also extended by x. They'll be one and the same thing. Whatever the displacement of the block, same will be the extension of the spring. So by the time the block is displaced by x, the spring is extended by x also. So what will be the relationship between v and x? That's the first thing we have to find. And from that, we have to find the maximum value of x.
Sir, max extension will be 2 centimeter, no?
Will be how much?
2 centimeter.
No. Now I'll give you a hint why you are thinking it is 2 centimeters. Because you're thinking that when extension is maximum, the acceleration of the block should be 0, right?
No, sir, I'm thinking that the external force, the force by gravity over here was 80 newtons. So to counter that,
the spring force.
K
So
constant.
that's exactly what you're saying. The spring force is equal to mg. That means acceleration is 0.
Yeah, sir.
But that will not be true, beta, because what is happening now? From your initial to that state now, the block is accelerating, right? Till it reaches 2 centimeters, the block is accelerating, right?
Yes, sir.
So by the time it reaches 2 centimeters, what is the motion of the block? It's not at rest, it's already got some speed downwards.
Yes, sir.
So it will extend the spring further now.
So it will extend it due to its further momentum, no?
Yeah, because of its momentum, it will continue. And once it goes past 2 centimeters, now the block starts to decelerate, because now your spring force becomes more than mg.
Yeah, okay, sir.
So the motion of the block will be in 2 phases. Initially mg is dominating, so its speed is increasing. But as it crosses that point where the two forces are balanced, now kx will dominate over mg, and it will start slowing down, and it will decelerate, and it will go to the furthest point where it stops for a moment. Then again it will come up. So this block will keep oscillating between the top position and the lowest position. Bye. Okay, anybody got the answers for this? Okay, so now we can see here that in this case, also we can do mechanical energy conservation, but there'll be two types of potential energy: gravitational potential energy as well as elastic potential energy of the spring. Okay, so initially when we just released the force, this was the situation, and this was at a natural length. Okay. Now after some time, let's say this has become L plus X. Okay, so by now the block has developed a speed V, which will eventually come to rest also, but in general, and the displacement of the block is also equal to X only, whatever is the extension of the spring. So from here to here, if we apply work energy theorem, but work energy theorem taking the earth plus the block plus the spring as a system, then we see that once again work done by external force is 0, work done by non-conservative force is 0. Okay. So once again our mechanical energy will be conserved. So change in kinetic energy plus change in elastic potential energy of the spring plus change in gravitational potential energy is 0. Okay. So going from this state to this state, you can see that when you implement this, people, you're following this, right? Okay. So kinetic energy is increased from 0 to half mv square. Potential energy of the spring has also increased. Gravitational potential energy is decreased. We get this. So this is the relation that we are getting between the speed and the downward displacement of the block. Okay, so this is the answer to the first part. And for the second part, you can see that X will become maximum when P is 0. The block comes to rest at the lowest position. So substitute that.
Sir, what is before energy?
What is before?
Energy.
Mechanical energy. Right? Why we are doing total mechanical energy conservation? Because this is 0. No? Understanding?
Yes, sir.
So mechanical energy in this case is the sum of the kinetic energy plus the elastic potential energy of the spring plus the gravitational potential energy. So because this is conserved, the change in this quantity is 0. No? Delta E is 0. So that's how we got the sum of these three things is 0, right?
Yes, sir.
Okay. Now when we solve this condition that, when the block reaches the lowest position, it comes to rest momentarily. So kinetic energy becomes 0. So by solving this, we get X is equal to 2 mg by K, which when you solve here will come out to be 4 centimeters because the weight was 80 newtons, right? And the spring constant was 20 newtons per centimeter. So this is answering that part, okay? And similarly, for the third part, you just substitute the value of X as, what was it? 2 centimeters in this equation and solve for B. And you'll get the answer. Okay? Just convert the units and all that. Okay, so hope this application was clear to all of you people.
Yes.
Yes, okay. So this is the main part of this chapter now, work energy theorem, especially with the emphasis on situations where mechanical energy is conserved. Okay. So please cover up to question number 42 in H.C. Verma. H.C. Verma's work by energy chapter exercise.
So could you please scroll up a bit to the third part of the question?
Yes. Third part of the question, you asked to find the speed v when x is equal to 2 centimeters.
Third as in the max extension.
Oh, maximum extension.
Yeah, I'm just writing everything.
And the first part's answer, I hope all of you understood now earlier.
Yes.
This external force is just balancing the weight initially. So that was 80 newtons. Okay. So yeah, this is actually the second part. This is the third part now. Okay, so hope this is clear, people.
Yes, sir.
Right. Okay. So please attempt up to this question number 42. Next lecture, we will discuss some of these questions also. Okay. So wish you all the best, people, and hope to see many of you during the lectures next week, because we're going to have quite a few offline lectures or doubt sessions at least. All right. So that's it for today, people. Wish you all the best. Have a nice day.
So just
Thank
one
you, sir. Bye, sir.
Thank you, sir. Bye.
Bye, sir.
So, sir, please present your screen.
Yes, sir, I'm writing.